Right. So can you, sorry, can you see the slide? Design and compensation of
Yes,
control
ma'am.
systems. Okay. Right. So, right. So in the last class, basically, what we did was design of control, not design actually. We had learnt about controllers, P, I, and D controllers and combinations thereof, right? So today we are going to go to the design and compensation of control systems. Now, as far as what I will be teaching today, and as well as if I cannot complete today, maybe in the next class, is concerned, this particular module will be taught from the book by N.K. Sinha, I believe, has the same method that I have outlined over here. But for this, of course, you would be requiring some basic knowledge about control systems, namely Bode plots. Okay, so I will be assuming that you do have some basic knowledge. If you have difficulty in understanding at some point, you can just let me know so that I go a bit slow or go a bit more basic, right? So today, the first slide that we will be having is this one. Okay. Okay. So, as far as control systems are concerned, control systems we've discussed earlier as well. From the very first class, I told you control systems are designed to perform or meet certain objectives. That is, they are designed for a specific purpose, right? So, a well defined or well designed can you still hear me? Temporarily lost the connection. Can you hear me?
Yes, ma'am.
So, okay. So, right. There was a problem with the connection, that's why. Okay, so some of such objectives are outlined over here. There could be more of such properties that the control system should be having. Okay, so one or more of such properties would be expected to be there within a well designed control system. So say for example, it should operate with as little error as possible. And when we are speaking about errors, here, if we refer to the static errors, meaning the steady state errors, we would be looking at tracking systems, meaning that systems which are meant to track certain, say, objects, etc., are expected to have as little steady state error as possible. Also, dynamic errors should be done. Dynamic errors means the error during the transient portion also should be small, meaning that it shouldn't have too much of overshoot and undershoot, or even if it has a certain amount of overshoot and undershoot, those should settle down or die down quite soon, right? So that actually comes under the second point, that is, it should, a well designed control system should exhibit suitable damping. The performance, system performance should not be affected by changes in certain parameters, because we know that all systems are actually, I mean, you will have a physical system. So when you are doing the design, naturally you've considered some values for the parameters, etc., and you've done your design. Now when you are actually compensator to the actual field, meaning to the physical system, then the physical system parameters in actual case may be changing. Say for example, you have an electrical circuit, so over there the resistance value may not be exactly what you have assumed it to be, or maybe it is being heated and the resistance value is changing. So even in the change, I mean, in the case that the parameters change, the system performance should not be considerably affected by such small changes in certain parameters. Small is, of course, I mean, sort of mentioned over here in the sense that naturally, if you design a compensator or controller for a control system, you cannot expect it to work under, I mean, if the system parameters change a lot, it will not be operating properly. That is understood. But for small changes in certain parameters, it is expected that whatever compensator we've designed would be working properly. And for that matter, the system by itself, even without the compensator, should be meeting the properties or specifications for which it has been designed. The well-designed control system should be able to mitigate the effect of undesirable disturbances. So here, the second last point mentioned changes in the parameters, parametric perturbations. The last point mentions the effect of undesirable disturbances, meaning that if some external signals are affecting the system apart from your desired signal, or what you call the command signal or reference input, apart from that signal as well, some other signals will be affecting the system, whether you like it or not. So, such undesirable disturbances, the system should be able to take care of that. Take care means what? It should still perform satisfactorily, even if there are disturbance signals affecting the system. So, that is a wish list. Wish list means that is what we can do. Not all systems will be having such properties, of course, that is understood. Now, what is compensation? So, a control system usually requires some adjustment so that various conflicting demanding specifications may be met. So, we have already spoken about this when we had done the preliminaries regarding PID controller design. Over there, I had showed you with the help of a second order system that the system requirements often lead to contradictions, meaning that the contradictions or conflicting requirements, which may not be possible to meet those conflicting requirements by using the system by itself. So what is required is that some external components, or either in the form of physical components or in the form of some sort of software, or whatever be the nature of such components, you can say. Basically, these are used to make the system, or enable the system to meet the conflicting specifications or demanding specifications. So such adjustment is called compensation, right? So I'll mention once again that such, compensators or controllers, whatever you call it, basically may either be physical in nature, meaning you may have some hardware, or it just may be some sort of software that you're using. So a computer program which is serving your purpose, it's giving you the desired signal at the output, you're interfacing it with your system, and it's serving your purpose. So physically it may, it's not essential that it's going to be some sort of hardware. It may be a hardware or a software, but this purpose would be the same. Whatever, same means whether it is realized by using physical components or realized just by using a plain computer program, the purpose that it serves would be the same. For example, meaning why compensation is used, maybe increase in the loop gain reduces steady state error, we've seen that, but causes deterioration in the transient performance. This we've already discussed when I was giving you the introduction to PID controllers. Thus compensation would be required. So now what we are going to see is, first of all, we are going to see the approaches, the general approaches to compensation, and then we are going to follow one specific method by which you can design a compensator given a control system. So that would be actually what we are going to do. So first of all, the configurations, meaning you may have a series or cascade compensator. Over here, you see that the compensator is in the forward path. I've mentioned this earlier as well. We were doing this when we mentioned about the PID controllers. So here, the compensator or controller is in the forward path. Here, GCS is denoting the controller block, and GPS is the plant block. So such sort of compensation is known as series or cascade compensation. Next, another configuration which is used for compensators is known as feedback compensation. So here you find that this HCS is the compensator block, and it's obviously in the feedback path. So the plant block is over here, GPS, along with the unity negative feedback, right? And then additionally, you have this compensator, which is a feedback compensator. We've already studied this without knowing the name, or without using this name, we've studied such a compensator already, that was derivative output feedback, right? So, or output rate feedback as we called it. So anyway, this is the same configuration as that one, but here we are generalizing or studying about the general names which are given to such compensators. So this is known as feedback compensation, where the compensator is inserted in the feedback path. Often what will happen is we will find that the compensator would have a combination of such schemes. So maybe you have one compensator in the forward path, another in the feedback path, and by combining those two, you are trying to meet the objectives for which the system has been designed. Now, as I already just mentioned a while back, the compensator, like the system components, may be an electrical, mechanical, hydraulic, pneumatic, or other types of device. So basically, um, when we are speaking about physical components, it may have any physical nature, as you can see, right? So some of which are mentioned over here. Electrical networks are often used as compensators. Now, the simplest among them are lead lag and lead lag lag lead networks. So we will be studying a bit about these, that is lead network, lag lead network, at least the compensators, in a moment. But before that, we from this slide we gain the knowledge that compensators may have any physical nature. What is not mentioned over here on this slide is that it may also be any other type of devices mentioned over here, but apart from that, you may have a simple software which is serving your purpose, right? So it is a computer which is doing your work of compensation, I mean. Now we come to the approaches to compensation. Now, approaches to compensation would mean that basically you visualize you have a system, the plant is already designed and is with you, right? And then you want some specifications to be met. So basically, what are the approaches, general approaches by which you may design compensators? So that is what is going to be spoken about next. So the okay, earliest approaches to compensation were based on modifying the frequency response of the forward path of a unity feedback system in such a manner that the performance of the closed loop system is satisfied. So it means that basically, if you have a system, you can get the frequency response, and then you may try to meet that. You may try to make that frequency response match with the response that you would be requiring for your system. So you know that, okay, after compensation, I must have such and such a gain margin, such and such a phase margin, and all that. So now, you have your system, and from your system, you see how much of phase margin and gain margin you have got, and then you try to use a compensator such that your requirement is met, meaning that you are able to change the phase margin and gain margin to meet your requirements. So basically, it is the frequency domain approach that we are speaking of over here. So for this method of design, the steady state accuracy is specified in terms of the error constants or error coefficients Kp, Kv, and Ka. The transient performance is specified in terms of phase margin, gain margin, maximum magnitude of the closed loop frequency response, etc. And the speed of response is specified either in terms of the crossover frequency or the frequency at which the maximum closed loop frequency is obtained. So basically, this whole approach that we are sort of just stating over here, we will go into a bit more of details of the approach in later parts, that is today itself. So basically, this first approach that we are speaking of is related with the frequency response of the system and the desired frequency response that you want from your system. So basically, and then you try to design a compensator such that it matches. So what has been mentioned over here is that for the method of design, basically steady state accuracy in terms of Kp, Kv, and Ka may be specified, and also the transient performance in terms of your phase margin, gain margin, etc. are specified. So It may be noted that although these quantities are related to the transient performance in an indirect manner, they may be conveniently determined from the open loop frequency response. So you would be noting that over here, I've stated transient performance. Transient performance actually refers to time domain response, right? Time response. But I mean, they are indirectly, the transient response is indirectly related to the frequency response specifications, namely maybe phase margin, gain margin, maximum magnitude of closed loop frequency response, and so on. So though we are speaking about the transient performance, meaning we are referring to the time response, in terms of the specifications that we have mentioned, those are frequency response specifications over here, because they are indirectly dependent on this. Now, another approach to compensation is through the root locus method. So you would have studied the root locus method already in the other part 2. I hope you've already done that or would be doing it very soon, I hope. So the root locus method, actually, in the root locus method, the root locus is shaped through the use of compensators so that the dominant poles of the closed loop system are at suitable locations. So let us say we have the system and you can draw the root locus for that system. So now there is a desirable root locus that you would be requiring for certain specifications to be met. So now you try to place your compensator poles and zeros at appropriate locations such that your root locus plot matches with your desired root locus plot, right? So basically, the method that is used is by using the root locus method. Of course, the basic is the same, meaning you have a desired set of specifications to be met, and for that, naturally, a particular, system should have particular root locus. So you, without compensation, meaning the uncompensated system, you can draw the root locus, and then you can try to place your compensator poles and zeros such that the root locus approaches the root locus that is the required one, meaning the compensated system root locus should be such that your original system, that is uncompensated system, is modified to meet the requirement specifications. Now another approach, so that was the root locus method. So a more direct approach to the design of control systems is to determine the transfer function of the closed loop system that will give a satisfactory performance. So maybe that you already know, okay, the poles and zeros should be like this, meaning these should be the locations of the poles and zeros. So you know the transfer function of the desired system, that is the compensated system, what it should be like. And you also have the uncompensated system transfer function. So you design a compensator which is going to make your transfer function match with the final one that you want. So the compensator is then designed so that the system is forced to this transfer function. Now the selection of the desired closed loop transfer function is the most important step in this procedure. Naturally, you must know what you really want. If you can pinpoint and say, okay, this is the desired transfer function that I want, then you can, you can design a compensator on your system, for your system, and use it so that you get the required one, right? So one must also be able to make the design physically realizable and economical. So I mean, in the process of designing a compensator, you should keep in mind that whatever you, say the compensator, say you have got a compensator transfer function, you've said, okay, this should be the transfer function of my compensator. It should essentially be physically realizable, right? Physically realizable, one of the important, aspects which is going to make the system physically realizable is that the transfer function should be um, either strictly proper or at least proper. Now, what is proper and strictly proper? What is the meaning of, say, a proper system, or for that matter, strictly proper transfer function? You would be familiar with these terms: strictly proper and proper. What happened? Okay, the denominator order should essentially be either greater than the numerator order are at least equal to the numerator order. You cannot have a system where the order of the numerator in the transfer function, that is greater than the order of the denominator, right? So such systems are not physically realizable. So basically, whatever you say your compensator transfer function is, that should be physically realizable and also economical. Naturally, I mean, if you want something which is not going to be economical, it would be a costly thing, and not many people would want your compensator even if you design it. So economical, it should be economical. The other desirable properties are insensitivity to small parametric variations, so small variations in parameters. So this actually refers to robustness, right? So basically, if you have designed a compensator, that compensator should have the property that even this, if the system has minor changes in the parameters, still your compensator is going to be insensitive to such small variations in the parameters of the system. Otherwise, what will happen is, say for example, you have your system and you've designed a compensator. So now after, I mean, after it is the system is actually working, minor change in the parameter due to some reason would actually result in the fact that your compensator is no longer going to work suitably. So that is something which is not desirable. So insensitivity to parameter variations is an essential or desirable property, you can say, for compensators. The term that is used for such insensitivity to parameter variations, small parameter variations, is known as robustness. So, I mean, those were some of the approaches, the broad approaches that are used for the design of control systems. So, we've actually, I'll just, I mean, uh, sort of summarize, not summarize exactly, just enumerate the methods that we've mentioned. One is the frequency response, that's on this slide. The other is the root locus method, this slide. Next is the method of directly, I mean, changing the transfer function somehow by using a compensator, right? So such are, I mean, these are some of the broad approaches which are used for compensation. So now we are specifically going to concentrate on the compensation using Bode plots. That is a frequency response method. So I'm sure you are already familiar with the method of Bode plots. You should have learned in your signals and systems in the second years. So basically, the compensator is going to be designed by using Bode plots. So the main attraction of this method is that one does not have to know precisely the transfer function of the plant to be controlled. So what we are saying over here is that basically, if you have a system, you can directly get the Bode plot without even knowing the transfer function of the system. I'm speaking about a physical system where you can experimentally try to obtain the frequency response. Now, as far as Bode plot is concerned, what plots are there? There are two plots in the Bode plot, two components in the Bode plot you would be recollecting. One is the magnitude versus frequency plot, and the other is the phase versus frequency plot. So now, I mean, in order to get the Bode plot, of course, I mean, if you know the transfer function, you can directly find the Bode plot by using some theoretical method, which you must have learned. The other method by which somebody who doesn't know the transfer function of the system can also obtain the Bode plot if he or she has the system and an experimental setup. So how is that done? We are going to see in a moment, right? So basically, the frequency response of the open loop transfer function is measured experimentally, and then I mean, once you obtain the frequency response, say you have obtained the Bode plot experimentally, so now you can try to reshape the Bode plot. How to reshape? You use a compensator which is also then going to be applied to your system, so the Bode plot will be changing. Changed Bode plot or compensated system Bode plot should be the one that is the desirable one for you, right? So that is the general method which, I mean, is undertaken in this method, that is compensation using Bode plots. Now, the performance criterion that we would be trying to meet by this method, that is using Bode plots, are as follows. That is, the steady state error coefficients may be specified, the phase margin or the gain margin could be specified, the gain crossover frequency and the phase crossover frequency may be specified. So in most cases, you would be given the steady state coefficient, maybe the Kp or Kv value is mentioned. Also, additionally, the phase margin and gain crossover frequency may be desirable specifications. So now, once these are mentioned, the the desired or required Bode plot would be more or less sort of it's specified in terms of these specifications. So now, if you have the Bode plot of your nominal system, meaning the system without the compensator, you can design a compensator such that you get your desired Bode plot, or at least the desired requirements, the performance specifications that are mentioned. So now I'll actually tell you how you can obtain the Bode plot by using an experimental setup. So you would be recollecting that the Bode plot actually, as I told you, consists of two plots. One is the gain plot or magnitude plot as we call it, and the other is the phase plot. So the magnitude plot means magnitude versus frequency. So now basically what that physically means, or how to physically get the Bode plot by using an experimental setup, is what I'm going to state over here. Please listen very carefully if you're not familiar with it, because actually we have an experimental in the control lab which shows you how to obtain the frequency response experimentally, but unfortunately for your batch you have not been able to go to the lab and must have missed out on that. Maybe one theoretical class you've got on that, just that. So anyway, so here basically what I've shown is the block in the middle that I've shown is some system. Over here specifically one system is shown. This is an inverted pendulum, but it is it is trying to denote a system. Whatever system you have, that will be over here. Now, how to obtain the Bode plot experimentally? So for that, first of all, you are going to require something in which you are going to see the signal. The output signal has to be observed. So for that, put an oscilloscope over here. You are familiar with oscilloscopes, I'm sure, in the measurement lab, in the control lab, even high voltage power system, all labs you would be requiring oscilloscopes. So we are using an oscilloscope. We would be requiring to use an oscilloscope to observe the output signal. Now, what to apply at the input so that we are able to get the Bode plot, right? So the first thing that the first of the two plots that I've mentioned is the magnitude versus frequency plot. So in order to obtain the magnitude versus frequency plot, and as well as the phase versus frequency plot, what is required is that the system is excited by using a variable frequency sinusoidal generator. So what this variable frequency sinusoidal generator does is that it generates sine waves. Okay, so sine wave signals are actually generated. But what sort of sine wave signals? Basically, the amplitude of the sine wave that is generated from this signal generator, the amplitude remains constant. So say for example, if I say an amplitude of 1 units or A units, capital A units, is what we have as the amplitude of the sine wave that is being generated from this variable frequency generator. Now, what else? What are the, two properties or two what do we call it, two parameters which actually describe a sine wave. One is the amplitude. What is the other one? The other is the frequency of the sine wave, right? So A sine omega t would be your sine wave. So basically over there you have the omega and you have your A. So A is the amplitude. So as far as this variable frequency sinusoidal generator is concerned, the sine wave that is being generated is going to be of a constant amplitude. But the frequency of the sine wave that is being generated would be, you can vary. There is provision over here to vary the frequency of the sine wave of this variable frequency sinusoidal generator. So for a particular frequency, say for example, if I now set the frequency of the sine wave signal at say 1 radians per second. Okay, so now the sinusoidal generator will be generating a sine wave with an amplitude of A units and a frequency of 1 radians per second. that is going to go and excite your system. You will be able to observe the corresponding output over here. Now, what do we expect at the output? If the system over here is a linear system, the output waveform is also going to be sinusoidal in nature, right? However, what will be changing is that, what might be changing is that the amplitude of the output waveform would not be matching, may not be matching the amplitude of the input signal. That is one thing. Also, the phase of the output signal may not be matching the phase of the input signal. So basically, we are going to get a sine wave at the output with a particular amplitude and phase, which, I mean, in general, will not be the same as the amplitude and phase of your exciting signal. So now, by observing the sine wave over here, what do we do? Say, for example, as I said, we have given over here a signal at a frequency of 1 radians per second. So, corresponding to a signal frequency of 1 radian per second, I've put in a particular amplitude, and the sinusoidal waveform is over here. So the output now I will be observing. So what in the output will I be observing? I will be observing, first of all, the amplitude of the output. So the amplitude of the output waveform by the amplitude of the input signal will give me how much amplification or magnification has occurred at 1 radian per second, right? So I'll repeat that. The amplitude of the output waveform is to be noted. As I told you, it's going to be sinusoidal, but the amplitude would be in general different. So that amplitude has to be noted. The ratio of the amplitude of the output waveform to the amplitude of the exciting signal is going to give you the amount of amplification or attenuation which has occurred at that particular frequency. What particular frequency? The frequency at which I've given the input sine wave. So it's, say, for example, 1 radians per second that I've got over here. So at 1 radian per second, the amplification or amplification is such and such, so A1 by A or something. Okay. So that is as far as amplitude is concerned for, say, 1 radian per second. Now, let me finish off the magnitude portion first, then I'll come to the phase portion so that it's easier for you to visualize. So I've got, with this, I've got the value of the amplitude corresponding to 1 radian per second. So I have my semi-log graph paper corresponding to 1 radian per second. I will put one point over there, which is the ratio of the output amplitude to the input amplitude, right? So now I change the frequency of the sine wave over here. Let us say I, instead of 1 radian per second, I make it 2 radians per second, right? So corresponding to that, again, I'll get the output waveform over here. It's going to be visible. And now I will also be getting the amplitude of the output waveform, right? So let us say that that amplitude is now, instead of A1 that I said earlier, that amplitude is A2. So A2 by A will be the amplitude corresponding to 2 radians per second. So I get another plot on my magnitude Bode plot, right? So I get another point on my magnitude Bode plot. Sorry. So like that, I can keep on changing the frequency of the sine wave that I'm using for excitation. Corresponding to that, I'll observe the output sinusoid amplitude, and I can, I mean, by taking the ratio in each case, if I have used an amplitude of 1 units, naturally, I mean, the amplitude of the output is the amplitude, because that by 1 is what we get. So for each frequency, I will get one magnitude, and I can put it versus the frequency on my Bode plot. So I get, if I cover an entire range of frequencies that I require, say from 1 radian per second, I've taken up to 100 radians per second. And for each, I mean, frequency over there, I've got one magnitude value. So I have got the magnitude versus frequency plot. That is one of the components of my Bode plot that way. So experimentally, you can obtain the magnitude plot of your Bode plot. Okay, I think over here only the you can just see the amplitude can be varied, frequency can be varied. What I wanted to show you is, in case you have forgotten or something, this basically is a typical, I mean, amplitude plot or magnitude plot. So magnitude on this side, frequency on this side. So what I said is corresponding to one frequency, you get how much of magnitude. So put it there. Then corresponding to another frequency, you get the amplitude, right? So that way, each time you get one value and you plot it. Plotted means you put the point on the Bode plot. So now by joining those points, whatever is there, you would be able to get the magnitude response, the overall magnitude response. This, of course, is for a specific system. But what I wanted to show you is this particular framework over here, where you would be able to get one point at a time by using that experiment, right? Similarly, now the phase plot. So phase response is another component of the Bode plot. So now again, by using the we had used a sinusoidal generator, and basically say for a particular frequency you have your input sine waveform. The output sine wave you would be observing as shifted. In general, it is going to shift by a particular amount of phase with respect to the input waveform. In fact, if you put in both your input and output at the 2 points in the oscilloscope and superimpose them, you would see that if, say, for example, this is the input waveform, the output waveform is going to be a sinusoid, but it's going to be shifted by a certain amount. So that will give you the phase corresponding to that particular frequency, whatever frequency you are exciting the system at for this particular, run of the experiment. That corresponding to that frequency, the phase difference, either phase lead or phase lag, is going to be giving you the phase. So you will get either plus phi or minus phi, and you can again plot that phase versus the frequency. So that frequency that you have excited at and the corresponding phase you can plot. So now each time I change my frequency, I get a different phase shift over here, either a lead or a lag, whatever be the thing. And corresponding to that, I would be able to, again, this is the phase versus the frequency axis over here. So each time I will get one phase over here, sorry, um, what have I done now? Okay, one phase value, and that can be plotted one point at a time to give us a complete phase plot. So phase versus frequency plot experimentally can be obtained. So that now, by now you must have understood that experimentally, even without knowing the transfer function, you can obtain the Bode plot, both the components, magnitude versus frequency, and the phase versus frequency of the Bode plot can be experimentally obtained by using such a setup. Sure. This, of course, I mean the same diagram that you had over there, only the variable frequency sinusoidal generator is shown a bit more closely. You can see the several things, and here this knob over here, you can say, is actually for the frequency. So basically you can change this by, first of all, selecting the range. Range is given over here. This particular sinusoidal waveform generator, the range is specified in hertz. So you see 1 hertz, 10 hertz, 0.1 hertz, 100 hertz, 1k, etc., etc. You can specify the range, and then 1 to 10 on this side, or 10, it's a bit more, I think. So anyway, so here you can, I mean, select a combination of this value, and that value will give you the frequency of the excitation signal, right? So now, once the Bode plot is obtained, how to do the compensation by using Bode plots? The first step in the design is to adjust the loop gain so that the steady state accuracy requirement is specified. So, is satisfied. So we will be observing that when we do actual numerical problems, you will be, seeing that in many cases, as I mentioned earlier, maybe the KP or KV or KA is the require, is specified, or maybe some sort of steady state accuracy requirement is there. So let us say that the steady state error should be equal to 0. So for that, now you try to find out what your KP or KV value is going to be, and from there, basically, the system gain you can, find out. In case the system gain is not specified, transfer function of the system may be given in terms of the general gain value, that is, some k is specified. I'll actually typically show you. Bode actually leaky usually, and it's a bit difficult. I'll just go to some next slide where ah, like this. So let us say the transfer function is specified in terms of k by s, s plus 5, s plus 10. So this is the transfer function. So first job would be to find out k by taking whatever requirement is given for the accuracy. So for the accuracy in this particular problem or example, kv is mentioned as 10. From there somehow calculate k for the system. So once you get the k, the whole of the transfer function will be known to you, because k is the only parameter which is unknown over there. So that is what I'm trying to tell you as the first step. Let me go back. So the first step in the design is to adjust the loop gain, that is k, so that the steady state accuracy requirement is specified in terms of is satisfied. Sorry, in terms of maybe kp or kv, that is steady state accuracy requirement is already mentioned. From there, you calculate the value of the loop, your gain of the system, that is k. Next, what you have to do is once the transfer function is known, the frequency response of the uncompensated open loop transfer function is actually calculated. Okay. So now if the requirement, that is the phase margin specification requirement, is not met, a compensator, maybe a lag compensator or a lead compensator, must be included in cascade in the forward path. So here we are limiting our discussion to only cascade compensation, meaning we are going to assume that the compensator is only in the forward path. So if the requirement, namely some phase margin specification, is not met, we would be requiring a compensator, requiring to design a compensator to attain the objective. The choice of the type of compensation depends on the gain phase characteristic at the desired gain crossover frequency. Sorry. So basically, I'm going to outline this method more quantitatively, meaning that you will then understand what exactly is meant by this. But uh, till now, you must have understood that what we require to do is, first of all, find out the value of the gain of the system, that is k. Next is find out the frequency response of the uncompensated system, because the transfer function is already known to you. Now, from the given requirement specification, maybe in terms of phase margin, you try to find out or design the compensator which is going to meet your performance requirement, right? So for finding out or designing a compensator, one thing, one sort of step would be to choose the type of compensator. So maybe there is a particular system requirement for which you would have to design a lag compensator, or another requirement where basically you would have to design a lead compensator, or maybe there is a third requirement where either a lead or a lag could serve your purpose. So you can design either of those. We will be seeing these, as I said, quantitatively, but the choice of the type of compensator is one step. Next is that you design the compensator. That means the parameter values of the compensator also have to be decided upon. So first of all, now we are going to come to this series, which is lead compensator, lag compensator, and lead lag compensator, etc. The first of which is known as lead compensator. So you can see the transfer function given over here. So GCS is denoting the compensator transfer function and is given by 1 plus S by A by 1 plus S by alpha A. So over here, this is the transfer function of the lead compensator when, of course, the alpha value is greater than 1. So now over here, the pole and the 0 has been plotted. You can see that. So the pole is located, you can see this is the real versus the imaginary axis. This is the S plane, as you call it. So basically one pole is located at minus A, the other pole is located at minus alpha A. So from here you just take out alpha, and or rather the other way around, you multiply numerator and denominator both by alpha A. So you can express it in this form, so that you can now see that the poles are located at minus A and minus alpha A respectively when alpha is greater than 1. So minus alpha A would be further away from the imaginary axis compared to minus a. So this requirement is very, very important. Alpha is greater than 1, right? So for this particular compensator, when alpha is greater than 1, the 0 would be closer to your imaginary axis compared to the pole. So in that case now, the first thing that we are going to do is we would be seeing the Bode plot, right? So in order to do that, the first step that is to be followed. So here I'm assuming that you have a preliminary knowledge of Bode plots. Here we are going to stick to the asymptotic magnitude Bode plot and the phase plot, right? So the asymptotic magnitude Bode plot, you would be familiar how to draw it. The first step in the drawing of the asymptotic magnitude Bode plot is that you find out what the corner frequencies are, right? So corner frequencies for this particular, I mean, transfer function, where are the corner frequencies? You can see that the corner frequencies, I mean, showing you this because basically this is in the standard form. So the first step in drawing a Bode plot would be, if you have, say, the transfer function given in the pole zero form like this one, you would have to convert it into the time constant form. If it is given in the time constant form, you can use that directly. So the first step would be to identify the corner frequencies. So here, say the numerator is in the form of 1 plus s tau 1, right? So 1 by tau 1 is going to be the corner frequency. So over here you find that tau 1 is equal to 1 by a. So 1 by tau 1 will be equal to a. So a is the corner frequency corresponding to this 0. So that is somewhere over here, right? So let us say that is this one, it's marked over here. Now the other corner frequency corresponding to the pole, again you have to find out. So 1 plus s tau 2, let us say. So tau 2 is equal to 1 by alpha a. So the corner frequency would be at 1 by tau 2, which is going to be equal to alpha a. So as alpha is greater than 1, the corner frequency corresponding to alpha a would be placed at a higher frequency compared to the frequency a. So basically over here, the two corner frequencies have been obtained to be at A and alpha A. So now what do we look at? We look at the rest of the transfer functions. So first of all, the first corner frequency, meaning the corner frequency which is of a lower frequency, is A. So A corresponds to, we'll go there and we'll see A corresponds to the 0. So corresponds to the 0 means what? As far as the asymptotic magnitude plot is concerned, till the frequency A, we will be having a 0 decibel value, and after the corner frequency A, the plot would be rising up at a unit positive slope, or a slope of plus 20 decibel per decade, right? And it would have gone on rising at plus 20 dB per decade had it not been for the pole. uh, just a moment. For the pole at alpha A. So now, I mean, the plot would have risen up at plus 20 dB per decade like that, but at the corner frequency alpha A, there is a pole. So pole means what? The plot is going to go down at minus 20 dB per decade. So going up at plus 20 dB per decade and going down at minus 20 dB per decade together is going to give you a 0 dB per decade, meaning a slope which is equal to 0. So basically this is the asymptotic magnitude Bode plot. Okay, so here on this plot you find that there are two plots. I had used MATLAB for doing the plot, that is why the actual plot also has remained, but as far as you are concerned and as far as designers are concerned, the asymptotic magnitude plot is sufficient, and in fact that is the plot which is used for designing, knowing very well that, I mean, the exact plot would be following the asymptotic plot apart from the values at the corner frequency. So at the corner frequencies, the magnitude is going to be uh, a bit different from the exact, that is the value of the magnitude of the asymptotic plot. By how much also is something which is known. It is going to be having a difference of 3 decibels. Okay, so basically when you have the 0 over here, it is going to be, the exact plot is going to be plus 3 dB added to this value of magnitude over here. On the other hand, where there is a pole, the plot is going to be down by 3 dB, meaning a minus 3 dB to be added to the plot which you have as asymptotic plot. So anyway, so this is the asymptotic magnitude Bode plot, which actually, now I'll tell you one thing, that is we would be requiring for design and compensation that we are going to do over here, we would be requiring to do the plots not on semilograph paper as you might have been doing so far, but, and also which is shown over here because I used MATLAB, I got the graph paper and the plot on the semilograph paper. But you will be requiring to do the plots on plain paper by using your pen only. So sketches on plain paper are sufficient. So asymptotic Bode plots, you can just, I mean, use the slopes and draw. It's going to be, I mean, not that difficult. Exact plots are not required. You should not draw the exact plots. It is not at all required, right? If we do require the exact values, we are going to calculate the exact values from the expression for the magnitude. So, I mean, numerical expressions will be there. From there, we can calculate the exact values. So, the exact values are not required for sketching the asymptotic magnitude Bode plot. Now, similarly, we can, I mean, find out the phase as well. So, as far as the phase is concerned, what is the expression for phase? What is the expression for phase corresponding to this your this transfer function? How do we find it? You would recollect that the method for doing the Bode plot is to put s equal to j omega and then find the phase. So phase contribution from the numerator would be how much? Tan inverse of your omega by a by 1. So that is tan inverse of omega by a. And then phase contribution from the denominator would be how much? Minus of tan inverse of omega by alpha a, right? So that would be the overall expression for the phase over here. Now, which is greater, tan inverse of omega by a or tan inverse of omega by alpha a? I had mentioned that alpha value is greater than 1. So corresponding to, I mean, your tan inverse of omega by alpha a will essentially, because in the numerator you have a larger quantity, that the angle contribution that you get from tan inverse of omega by alpha a will be essentially lesser than the angle contribution from the numerator. So that if the overall expression for the phase is tan inverse of omega by a minus tan inverse of omega by alpha a, for all frequencies apart from the frequency equal to 0, that is when you put omega equal to 0, what would be the value of the frequency? It is going to be from the tan inverse of numerator, it will be tan inverse of 0. From the denominator also it's going to be tan inverse of 0. So tan inverse of 0 minus tan inverse of 0 will give you a 0 phase, 0 degree phase over here, right? Incidentally, the phase plot can be done in either degrees or radians. Here I've shown it in degrees, but if you do it in radians, I don't mind as well. So the phase plot corresponding to 0 radians per second frequency can be just put as a point 0. Of course, I mean, in your semilograph paper, you will not find 0 frequency. So what we would be referring to is a very low frequency. There, the value of your phase is almost equal to 0. Similarly, now at all other frequencies where omega is not equal to 0, what will be the contribution to the phase? So phase will be now again tan inverse of omega by a minus tan inverse of omega by alpha a. So basically now you have the contribution from the 0 is going to be greater than the contribution from the pole. So the overall phase contribution will be a positive value, right? So now, I mean, that is why you see the plot is actually going to the positive side. From the 0, it's going to the positive side. Now, at omega tending to infinity, what would be the contribution, what would be the phase value from this? You find that I've I'm repeating the expression for the phase, which is tan inverse of omega by a minus tan inverse of omega by alpha a. So when omega tends to infinity, what would be the value of the contribution from the numerator? Tan inverse of infinity, which is how much? It's pi by 2 or 90 degree, right? And from the denominator, how much do you have? You have again tan inverse of mm, infinity, which is 90 degrees. So 90 degree minus 90 degree, it will mean a 0 degree phase. So the nature of the phase plot would be that it's starting from 0, going to the positive side, and again coming back to 0 at a very high frequency, say omega tending to 0, it's going to be coinciding with 0. So this is the nature of the Bode asymptotic magnitude plot and the phase plot from the transfer function, that is a lead compensator. Incidentally, the name lead compensator comes from the phase lead that you observe over here. So positive phase means lead, negative phase means lag, right? So basically this is the transfer function of the lead compensator. That's what it's written over here, as the compensator provides a phase lead at any frequency omega apart from 0 and infinite frequency. It is called a phase lead compensator, right? And the pole 0 location is exactly as shown over here for a lead compensator. Values may vary, but the relative locations are, they would have to remain the same, meaning the 0 should be closer to the imaginary axis compared to the pole, which is going to result in the magnitude and phase plot that is shown over here. The nature of the magnitude and phase plot will be like this. Achha. So here basically certain things have been written. Usually I use the slideshow mode, and these come on one by one, but nevertheless this is the compensator transfer function. So the you can see the gain at low frequencies is 0 decibels, that is this one. Gain at high frequencies, now okay, so gain at high frequencies you have to find from here. So how do you get that? You find that at high frequency means basically omega tending to infinity. How will you find what the gain value is at high frequency from here? You will have to, how do you do it? You will have to divide the numerator and denominator both by, if you, I mean, visualize s equal to j omega, you would have to divide by the omega, right? So once you do that, here you will be having 1 by omega and plus j, here you will be having how much? 1 by a, right? And in the denominator, if you divide by 1 by omega, you would be getting, divide by omega, you would be getting 1 by omega plus j into 1 by alpha a, right? So from this now, when omega tends to infinity, what happens? 1 by omega over here tends to 0. Similarly, 1 by omega over here tends to 0. You will be left in j are there. So you will be left with what? You will be left with only 1 by a by 1 by alpha a. So that when you evaluate that, you will be seeing that at a very high frequency, the value of the magnitude is going to be equal to alpha. So if you plot it in decibels, you need to take the 20 log to the base 10 of alpha, so that basically the value of the magnitude at very high frequency is going to be 20 log of alpha. If you are doing the asymptotic plot, the value, it's going to be a straight line, so the magnitude will be constant over here. The value of that constant is going to be 20 log to the base 10 of alpha decibels, right? So that is shown on this slide. So gain at high frequencies is 20 log alpha decibels. Whenever I say log, I mean log to the base 10, not natural log, right? So now coming to the phase plot, the phase is almost 0 at low frequencies, as I mentioned. Now it is going to rise. For other frequencies it is going to have a positive contribution, so it is going to rise and then it's going to again fall and come to zero in the high frequency, right? So somewhere between the two corner frequencies there will be a place or a frequency where the phase value is maximum, right? So the maximum phase is obtained at some point, some frequency between A and alpha A, which are the two corner frequencies. The phase, of course, is almost zero at high frequencies. If you take a higher frequency, you will see that it's going to tend to asymptotically tend to zero value. So now, where does the maximum frequency, maximum at which reframe the question, at which frequency does the maximum phase occur, right? So basically, mm, as far as this is concerned, naturally, if you get the expression for phase, from there you can find out where the maximum phase occurs. How do you do it? You have to take the derivative, first derivative, and then put that equal to zero. Solve for omega, that will give you the value of the frequency where the maximum phase occurs. Now, just by looking at the plot and from symmetry, because there is only one pole and one zero in this particular transfer function, basically the plot is going to be symmetric in nature. Symmetric in nature means what? It's going to, this is the corner frequency A and this is the corner frequency alpha A. From this point to the next point, basically, it is going to rise up uniformly and then fall uniformly, in the sense that basically the maximum phase is going to occur actually midway between these two frequencies, that is A and alpha A. Now, what value of frequency would that mean? So, midway between A and alpha A, how much would be that value? Now, if we had a linear scale over here, midway would mean that you take the sum of the two and divide by 2. That would mean that the average of these would give you the value of the midpoint, right? But here we have not a linear scale, but we have a logarithmic scale, right? So this is exponential in nature. So now what would be the value of the midpoint, this frequency over here? Basically, it is going to be the geometric mean of the two frequencies. You can verify that, meaning that, say, for example, if you have a frequency of, say, 10 to the power 0, which is 1, and another that is 10 to the power of 2, that is 100, the point that is midway between 1 and 100 is actually 10 to the power of 1, which is the geometric mean of these two, you can see. So similarly, if you have A and alpha A, the geometric mean is going to be, whole under root of this into this. That is basically the midway. So omega m, that is the frequency at which the maximum phase occurs, is equal to, it's going to be given by, equal to is not given over here, but it is going to be midway between the two frequencies, and we will see that it's going to be the geometric mean. So it's going to be A root alpha, that I think is on the previous, on the next slide. So that is actually worked out over here now. So whatever I was saying regarding the calculation of the phase is actually shown on this slide till there, as well as the calculation of the maximum value, meaning the value of the frequency where the maximum phase occurs. So GCS, that's compensator transfer function, is given over here. So S equal to j omega you put, and then write the expression for phase. So phase is equal to tan inverse of omega by A minus tan inverse of omega by alpha A, whatever I was saying. Combine the two tan inverses together, because we actually want to find the derivative, so we have to do it over here. Combining, you have this, and then further simplifying this and this. So now you have to find out where the phase becomes maximum. So take the you can what you do is, you have to take the derivative of this and equate it to 0, and that will give you the frequency. If you solve then from there, it will give you the frequency at which the phase is maximum. You can work that out. I'm not showing the details of that portion of the working out, but please verify it. So the phase is maximum when, now that is found out as omega by A is equal to alpha A by omega, so that the value of the frequency where maximum phase occurs, denoted as omega m, is equal to a root alpha, right? And now by plugging in this value of frequency, you can actually obtain the value of the maximum phase as well. So that is done by putting the omega value over there. You can get it as this. So this is the value of the maximum phase, right? Denoted in terms of tan inverse, the same thing expressed in terms of sine inverse. So now, what we have said over here is that it may be noted that the maximum phase lead produced by the lead compensator is less than 90 degrees. So over here, basically, I mean, this plot is going to go up and then go down. But since we have, I mean, the phase lead coming as this difference between these two phases, it is never going to be equal to 90 degree. So it is essentially going to be the maximum value of the phase lead is that is obtained from the lead compensator will essentially be less than 90 degree, right? So in practice, the value of for alpha values of alpha greater than 20, sorry, let me reframe that. Uh, in practice, the maximum amount of, I mean, phase lead that you may obtain from a lead compensator is given over here. That is around 65 degrees. That will be obtained only if you obtain, I mean, if you use an alpha value which is greater than 20. Sorry, which is almost around 20. So that will give you the value which is uh, 65 degrees or so, right? Now, if you use value of alpha which is greater than 20, what will happen is that basically these, the pole and the zero will be, I mean, shifted far apart, and such, I mean, one will become sort of what we call a non-dominant pole. The other, I mean, the pole will become a non-dominant one rather, and such values are seldom used. So basically, what is done is alpha value which is at the most equal to 20 can be used, corresponding to which the maximum phase lead which can be obtained is around 65 degrees. But any phase lead greater than that cannot be obtained from a physically realizable lead compensator. So even if you are using a lead compensator, you cannot say, okay, I'll get 80 degree of phase lead from my compensator. No, in such a case, maybe you would opt for two compensators or something, but not from a single compensator, which is likely to give you not more than 65 degrees of phase lead. Achha. Do you have a class after this? Just now, that is. When is your next class? Do you have a class after this? Otherwise, I'll just continue for some time so that I can
No, ma'am.
finish considerably. Okay. So, okay. So now, I mean, we are going to derive certain sort of expressions which will be helpful for our design. So till now, we have not done any design. That was just a lead compensator that I've shown you. Similarly, I'll show you a lag compensator, but later. So for the lead compensator now, certain sorts of expressions would be derived by means of which we would be able to sort of go towards the goal of designing a compensator for our system. So till now we found out the expression for the phase, and from there the maximum amount of phase lead that we obtain, the frequency at which we can obtain the maximum phase lead, that much has been found out for a lead compensator. So now we will just make certain sort of assignments, assignments meaning that we are going to say that certain notations are going to be used, from where, I mean, with the help of which rather we are going to sort of find some useful expressions which are going to be used for the design. So given values of a specified phase lead phi c, so let us say that we require say 50 degrees of phase lead from our compensator. So we denote that phase lead by phi suffix c, and say we require some amount of gain from the compensator that is denoted as m suffix c, right? a latecomers coming in now. Okay, so those are the notations respectively used for the phase lead and gain to be obtained from the lead compensator at a particular frequency omega c. So let us say that the requirement is specified already. So we require to get a phase lead phi c and a gain mc at a frequency omega c. So now, it is possible to design a compensator for such a requirement. So for that, certain expressions are going to be derived, and that's what we are going to see over here. So first of all, look at this right hand side block over here, this one. Okay, so let the magnitude of gj omega c be denoted as a, right? So what is the expression for magnitude? Let me show you the transfer function. So this is the transfer function. You put s equal to j omega. Now what is the expression for magnitude corresponding to this transfer function? Can anybody tell me? You've put s equal to j omega. So you now have a complex number at the in the numerator and another complex number in the denominator. What would be the overall magnitude from here?
Ma'am, root over 1 plus omega square by a square divided by root over 1 plus omega square by alpha square is square.
Yes, right. Very good. So that would be the overall expression for the magnitude, right? So since you have a root over in the numerator as well as a root over in the denominator, in the expression for magnitude, I'm saying basically the assignment that we put over here is given. So the magnitude of gj omega c, whatever you've mentioned, that is root over of the magnitude of the numerator by root of, sorry, not root over of the magnitude, the overall expression for the magnitude of the numerator and by the expression for the magnitude of the denominator. Basically, the whole of it is denoted as A. So the magnitude of gj omega c transfer function is denoted as A, so that A square is equal to C. So C is again, let, it's part of that let. So let A square equal to C. So when you put A square equal to C, that root overs will actually, you can get rid of in the expression for magnitude, because A inherently will be having those root overs, but A square will not be having it, right? I hope that's clear. So now, if get back to what the notations that we had used, the gain that we require is denoted as MC, right? So MC is the gain in decibels that we require from our compensator. So MC is equal to 20 log to the base 10 of the magnitude, that is A, right? So this, say we have a required magnitude, a magnitude that is required. From there we can try to find out A by using this method. So MC by 20, if you take and then 10 to the power of that, is going to give you the value of A, right? So basically what we try to do is, let us say MC is the gain that is specified. From your compensator you require a gain of MC. So A is equal to A to the power of MC by 20. Why I've put over here, right? So MC, which is the magnitude, is equal to, the magnitude we've put over here as A, but this is not in decibels. So convert that to decibels, that is going to be equal to MC, right? So from there, A is equal to A to the power of MC by 20. So that if we square both the left hand side and the right hand side, A square is equal to 10 to the power of MC by 10. So that it means that A square is C. So C is equal to A to the power of MC by 10. So we have, just made certain assignments and then arrived at this expression. You will realize why we are doing all this when we actually find the expression, and it eases our task of designing. It is going to make the task of designing much easier. That is why we are trying to uh, obtain certain simplified expressions. Also, now coming to the left hand side over here, we are assuming that tan of the phase requirement from the compensator, that is phi c, is denoted as q, right? So now again, I mean, from the expression for the phase, we had actually written, we'd already written the expression for the phase. So this was the expression for the phase, which was combined together to give us this one. So tan inverse of this overall thing is the phase from our compensator. So basically tan, now if we say that, okay, the required phase from the compensator is phi c, and tan of phi c is equal to q, then in that case what we will be getting is, that step is not exactly written over here. What would we get? Tan of phi c is equal to basically this, right? So now, I mean, this whatever we have over here, in whichever form, this one or this one, right? So tan of phi c is equal to this. So now another, I mean, substitution has been made. That is, basically we've denoted omega c by a as capital omega. So from the expression that you obtain from this, um, from this, what will we obtain? Tan of phi c is equal to omega c by a minus omega c by alpha a by 1 plus omega c by a into omega c by alpha a. That's the expression. So from there now, omega c by a is denoted as capital omega. If you do that, and then, I mean, look at the overall expression, tan of phi c boils down to capital omega, where capital omega is omega c by a, capital omega into alpha minus 1 by omega, capital omega square plus alpha. So that is the overall expression that we obtain for q, which is denoting tan of phi c, right? I hope that is clear. If not, please let me know. I'll repeat again this particular thing. So y q is equal to this. Okay. So now coming back to our expression for the magnitude, which was already written on this side, c is equal to 10 to the power of mc by 10. So that is written over here. Now what is written over here is from the expression for magnitude. So expression for magnitude, you've already told me for this transfer function, right? So it is going to be root over of 1 plus omega square by a square by a whole by, that is root over of 1 plus omega square by alpha square a square. So that c square will be equal to that magnitude square, so that the root will not be there. So that is what has been given over here. So c square now, I mean a square. So a square, which is equal to c, is given by this, which is the square of the overall magnitude. Okay. So from here again, this, that is capital omega, has been substituted wherever we have omega c by a, and it has been written in this form, right? So from here directly, I mean, collecting terms, etc., containing omega square and then dividing and all that, we arrive at this, that is capital omega square is equal to a alpha square whole into c by minus 1 by alpha square minus c. So this comes directly from there. So basically this is one of the expressions. The other expression that we are going to, I mean, take is now coming from this term, that is, we have q is equal to capital omega into alpha minus 1 by capital omega square plus alpha. So if we, I mean, multiply this denominator to that side, we get, and then yes, um, and then square it, I think. So okay, square na. Q into squaring this, as well as squaring, so I mean, and then squaring the overall expression, right? So q square you have, and then this denominator multiplied on that side whole square is equal to this right hand side, that is omega square, capital omega square into alpha minus 1 whole square. So I mean, the same expression by multiplying with this denominator, and right hand side and left hand side by that denominator, and then squaring will give you this expression, right? So from here now, I mean, and then substituting for capital omega square from this, in this expression, we obtain an expression which does not contain capital omega square but is an expression in q alpha c. Okay, so those are the quantities that we have over here, parameters that we have over here, but not capital omega, which we have substituted from there, right? So now, I mean, just trying to collect terms containing, so this, I mean, is an expression where you find several things are there. So now we try to collect terms such that it becomes a quadratic in alpha. So, I mean, terms containing alpha square are collected together. So this is what you get, terms containing alpha, this is what you get, and also, I mean, terms containing which do not contain any alpha are the constant terms which are over here. So alpha is greater than 1. Okay, so alpha is greater than 1. We had mentioned for a lead compensator, alpha has to be essentially greater than 1, otherwise the relative position of the pole will not be to the left of the position of the 0. I'll just show you what I mean over here, and mention this one. So alpha essentially has to be greater than 1, isn't it? Because otherwise the pole would have gone to the this side, which would not have made this system a lead compensator. It would have become something different. So for a lead compensator, alpha is essentially greater than 1. So now, I mean, realizing that, and then, I mean, you sort of collect terms containing your alpha square and all that. So, I mean, why we are doing it is that, I mean, we are assuming that alpha is equal to 1 is not valid, right? Otherwise, we would not have been able to divide by this alpha minus 1 whole square. You can see from the left hand side and right hand side have been cancelled out. So if alpha is equal to 1, we could not have made that cancellation for obvious reasons. But since alpha is greater than 1, that is why that cancellation has been done, and then it has been written in this form. So now we have with us an expression containing a which is a quadratic in alpha, right? So something into alpha square plus something into alpha plus something into that is a constant, that is not something into, this is a constant, is equal to 0 constant in alpha, that is, there's no term containing alpha. So basically this is a quadratic in alpha. So now if, say for example, if we look at the coefficients, what do they contain? This coefficient contains q. What is q? Q is tan of the desired phase lead that we want. So if phase lead is specified, phase lead that we want from a compensator is specified, tan of that you can take, and that is going to give you your q. So q is something which is known to us, right? Similarly, what is mc? Mc is the gain that we want from our compensator. So that is going to be given to us, or you have to decide prior to designing. You have to know how much of lead you are, how much of gain you want from your compensator. So if mc is known, then your value of c, which is equal to 10 to the power of mc by 10, that is also going to be known. So c is also something which is known to us, right? So this overall coefficient is, I mean, something which is known. It's going to be resulting in a single constant if you evaluate that. Similarly, over here, the coefficient of alpha contains q and c, which are both known. So that is also going to give you one numerical value. Here, this constant term also, you have q and c only. So you can actually put those values and evaluate. So basically, you are going to get a numerical which is a quadratic in alpha. You can solve for alpha from that quadratic, and that is going to give you the value of alpha for your compensator, right? So basically, from there, the lead compensator can be designed. Now, we still have a few more steps. Okay, so this quadratic, now we want that the value of alpha is obtained. So for the value of alpha, how much is the value of alpha? Till now we know that alpha should be greater than 1. So in any case, alpha should have one unique positive real value, right? So basically, I mean, that can be obtained if and only if, okay, so q was what? Q was tan phi c. Phi c means what? The phase lead. So if phi c is a phase lead, q is essentially greater than 0, and that is there. Similarly, C is the magnitude. So in the lead compensator, we've seen that the value of the magnitude was, if you look at that, it's either equal to 0 at very low frequency or it is a positive lead. So again, C is also going to be a value which is greater than 1. So basically, acha. So now from the quadratic also, we can say that uh, we will get only one positive real solution for alpha if and only if q is greater than 0, c is greater than 1, and as well as this is valid, because you can see that, I mean, the coefficient over here cannot become uh, cannot become negative. So for that, you can see that c quadratic will have only one positive real solution for alpha if and only if, okay, first two are actually implied for a lead compensator. As I told you, q is greater than 0 and c is greater than 1. So basically, the last one, that is this condition, is the only condition that is necessary and sufficient for the existence of the lead compensator, that will give us a satisfactory, I mean, that will satisfy the requirements. So basically, I mean, this third one is the only, I mean, thing that we have to check and see whether it's valid. If it's valid, then basically we will be able to get a lead compensator. We can determine the value of A as, now, I mean, we put the value of alpha, we already know the value of alpha. So your value of MC, you see, is 20 log to the base 10 of A, and I mean, C value, these are all known things, right? So basically, now once alpha is known, uh, okay, C is equal to, C expression for C is equal to MC by 10, where MC again, I mean, has been put over here. So C is equal to, and this one, C is equal to this. So from here, basically, the value of A can be obtained. So from that expression for C that was already stated, we, I mean, take the rest of the things on the other side and just see what the value of A is going to be. So A in terms of omega C, alpha, and small c. So basically, this directly results from this one. So from the from your given values of phi c, mc, and omega c, you would be able to solve for alpha as well as get the value of A by using this particular method. So we will do one particular, I mean, direct problem. Direct problem means that given the values of phase lead and gain, we would be designing a compensator. So let me read out this question first. I will be requesting you to work it out in your exercise books parallelly with me. Now, the example, of course, it's worked out, but let us see how to do it. So determine the transfer function of the lead compensator that will provide a oh God, provide a phase lead of 45-degree and gain equal to 10 degrees of omega equal to 8 radian per second. So for this particular problem, we find that the, I mean, the transfer function of the lead compensator has to be found out. Transfer function of lead compensator means what? You would be recollecting that transfer function is in the form of 1 plus s by a by 1 plus s by alpha a. So what are the parameters to be found? A has to be found, alpha has to be found, right? Now what are specified for our particular problem? For our particular, sorry, for our particular problem, the phase lead from the compensator that we require is specified, as well as the gain to be obtained from the compensator is specified in decibels, as well as the frequency where we are going to put our compensator is also specified. So basically for our problem, we have with us phi c, which is the desired phase lead to be obtained from the compensator, that is specified as 45 degree, MC, which is 10 decibels, that is the gain to be obtained from the compensator, as well as the frequency where the compensator is to be placed, that is omega c, is given as 10 radians per second. So those are the given things. So here I come to this slide, that is phi c is equal to 45 degree, MC is equal to 10, and omega c equal to 8 radians per second. Those are already given to us. So from there now, how would we proceed? So the first thing that we would be doing is we would be finding out we would be requiring to actually frame the quadratic in alpha and then solve for alpha, and then once we get alpha we would put that in the expression for a and get the a value. So alpha and a are the two parameters that we require. Let me mute you just a minute. Okay, so yes, so basically phi c, mc, and omega c are given. So from there, first of all, we can find out what q is going to be. Okay, so what is q? Q is equal to tan phi c. So how much will be q for us? Just do it and tell me. How much will be q? What happened? Q is equal to tan phi c, isn't it? Q is equal to tan phi c. Okay. So how much is your q?
One.
What happened?
Ma'am, one.
Right. And yes, so q is known to us and mc is given as 10. So now c is equal to, you can see, just to recapitulate, C is, yes, C is also 10 to the power of MC by 10. So MC is specified as 10 decibels for us. So that we already have got our values of 1, right? 10 to the power of 1, you mean, I think, right? So basically, uh, because C is equal to 10 to the power of MC by 10. So MC is equal to 10. So 10 by 10 will be 1. So C is equal to 10 to the power of 1. So basically, we will be having uh, this, that is your C value is equal to 10. Sorry, just a moment. Yes, C value will be equal to 10. So now if we get that, we can actually try to put that in our quadratic. So this is the expression for the quadratic. So in the expression for the quadratic, you already know the value of q and you know the value of c. you can just put those over here and say what the first coefficient is going to be, what the second coefficient is going to be, and what the constant value is going to be. And then from there you can try to solve the quadratic. So I hope you've understood how to do it, very simple and easy way. So the coefficients have been calculated over here. You can go through your notes, it's going to be there. So first coefficient happens to be this, the second one, and the third one. So okay, so this is the quadratic, right? So basically from there now you can try to solve the quadratic. So basically after solving the quadratic, you arrive at two possible values for obvious reasons. Now alpha is essentially positive and for that matter greater than 1. So alpha will be given as this, that is your obtained as rather the positive value of these two, that is equal to 6.28, right? So once now the value of alpha is known, you recollect that expression for A, which had the omega c and the alpha and the c. So this expression you can put in. Omega c is also known to us, it's given, it was given in the problem, that is 8, right? And then from there we've already obtained alpha value, and c also is known, so just putting those you get the value of A. So now, I mean, since this was a direct problem means what? The frequency at which you are placing your compensator is given, how much of phase lead you want from your compensator is also given, how much of magnitude you need from your compensator is also given. So given all those things, it is, I mean, you can just now put that in the expression for the lead compensator, which was, if you recollect, sorry for switching slides, but this one. So alpha and A are already known to us. So just putting that in this will give you your lead compensator, right? So the lead compensator happens to be this. So please verify that and the whole thing at your leisure and see that this is the compensator. However, what we have done till now is not actually the design by itself. We will proceed to the design, but I mean, till now we have just seen that by using the expression that we have found, it is possible to design, or rather, it is possible to find the value of the numerator and denominator, and hence the transfer function of a compensator, lead compensator, given that we are sure about how much of lead we want, how much of magnitude we want, and at what frequency we want that compensator to be, right? So now, I mean, we proceed with the lag compensator. So in the lag compensator, basically the okay, so it's given in this form. It can be given in two forms. So one is this one, the other is this one. So this, in this form, basically beta is lesser than 1, or rather, if you, I mean, to simplify matters a bit, the pole and the 0 are located in this fashion. That is, the 0 is, value of the 0 is greater than the value of the pole, right? So basically, I mean, this is the pole 0 location of the lead of the lag compensator. And you can express it in either of those forms. This is in the form where you are expressing it in terms of beta and B, and I will be, I mean, expressions will be derived with respect to beta and B only, where beta is equal to 1 by alpha and B is equal to alpha A. So, I mean, correspondence can be seen between these two forms, you can see. So now, I mean, for a lag compensator, since you have the compensator is in this form, and then you can actually, I mean, put it in the time constant form, get it in the time constant form, and hence find your corner frequencies. You will find that the corner frequencies are at beta B and B respectively. Since beta B, I mean, corresponds to, since beta is lesser than 1, beta B is the lower frequency of the two, that is of B and beta B is lower. So now beta B corresponds to the pole first. So, I mean, the magnitude, I mean, it's starting at a constant magnitude, that is 0 decibels, and then it is going to go down from the first corner frequency, which corresponds to a pole. It is going to go down at a minus 20 dB per decade slope, that is the asymptotic magnitude plot. And then from the next corner frequency, we have the 0 coming in. So that 0 means a plus 20 dB per decade, which is going to be added to the minus 20 dB per decade, and finally you get a constant value over there. So basically, this is the asymptotic magnitude Bode plot. The value of the magnitude at very high frequency also you can obtain by a similar method similar to what we had outlined earlier. So basically, from there you would be able to see that the value of the magnitude over here is given by either beta if you are using the absolute scale, or 20 log to the base 10 of beta if you are using the decibel scale. Similarly, the expression for the phase can be found out from here, from the numerator and denominator. If you put s equal to j omega and then take the tan inverse of the phase contribution from the numerator minus tan inverse of phase contribution of the denominator, and then basically you will see that the phase is going to be having a plot which is like this. So at low frequency the value is going to be almost equal to 0. At a high frequency it's almost going to be equal to 0. For all other frequency there is going to be a negative contribution in the phase, because you will see from there itself, like I told you for the lead compensator over there, we showed that essentially it's going to be positive in the lead compensator. The contribution of phase is going to be positive. Here, since it is a lag compensator and you have this beta b in the denominator where beta is lesser than 1, essentially the contribution to the phase will be negative, like this, right? So basically this will be the nature of the Bode plot. Please, I'm trying to rush through a bit because we are almost towards the end, very few classes left as such. So basically, please try to verify and understand what I have said. Okay, so essentially there will be either a lag for all other non-zero or frequencies which are not equal to infinity, not very large. Essentially it's going to be lag. So the nature of the plot is going to be like this for the phase. So now for the lag compensator, again an expression, just again substituting or just assigning q equal to your tan phi c, and then your this c is equal to 10 to the power of mc by 10, like we did earlier as well. So and then finding out expressions which are similar to that done in the case of a lead compensator, we arrive at a quadratic in beta. Okay, this derivation has not been done in details in your slides, but you can actually verify that this is what you would be getting. So here again, you would be, if you know q and if you know c, it is a quadratic in beta, and you can solve for beta. And once you solve for beta and get the value of beta, b can be obtained by using this expression. So till now, whatever derivation I have done, derivation of course you have to go through and understand and all that. But now the main the focus would be to use those expressions to find out the compensators and do the design. So till now, I'm repeating, till now we have not done any design. Mechanically, we've done certain things. We found out expressions, and given certain values, we can find out the compensator. Similarly, for a lag compensator, now a numerical is shown. Phase lag of 50 degree is required, and attenuation of 15 decibels. Why is it written as attenuation? What will be the value of the attenuation? Value of the magnitude. If attenuation of 15 dB is mentioned, the value of the magnitude will be minus 15 dB. Okay, so and at a frequency of 2 radians per second. So we'll see that what is given is that lag means phi c is equal to minus 50 degrees, because a phase lag of 50 degrees is what has been mentioned as the requirement. Magnitude of the compensator required from the compensator, gain required from the compensator, is equal to attenuation of 15 dB, means minus 15 decibels at a frequency of 2 radians per second. So these are mentioned. So once these are mentioned, now you can find the value of q from this and c from this, and then put it in the quadratic, solve for beta. So that is what has been done over here explicitly. You can see the working out. Q is equal to, here this minus sign you have to remember, and that has to be taken, because otherwise when you substitute in the expression for the quadratic, it's going to become wrong. C also, is calculated on the basis of the value of MC. MC is minus 15 decibels, so that minus is again important. So if you miss out on that, you will get a magnitude which is not going to be an attenuation. So over here, once you calculate, so you can see it is attenuation is lesser than 1, isn't it? Earlier, for a lead compensator, we got the magnitude value greater than 1. Here it is lesser than 1, which is what is indicating that it is an attenuation. Excuse me. So from here, now the coefficient values have been calculated and the quadratic in beta has been framed. This is the quadratic in beta from where you solve and get the values of beta. So beta you would be recollecting is going to be lesser than 1, and that is the value which is taken over here. Lesser than 1, but it cannot be negative, isn't it? Because you would be recollecting that if I just show you the pole 0 locations. Acha. This is minus b, this is minus beta b. So beta is essentially lesser than 1, right? But can beta be negative? What will happen if beta becomes negative? What will happen to this pole 0, I mean the pole location if beta becomes negative?
And pole will be on right hand side, the system will be unstable.
Yes, very good. So you can see that beta essentially has to be positive. It's lesser than 1, but it has to be positive so that we have a, I mean, compensator which is a stable one, right? So beta will be lying between 0 and 1, but not, I mean, negative. So you have to, after solution, uh, after solving for beta, you cannot take the negative value, has to be discarded. You will get one negative, you can see from here. So negative has to be discarded. You will have to take a positive value which is lesser than 1, which we have got one of those over here. And so that is the value of beta. Once you get beta, substitute that in the expression for b, and you would recollect that expression for B is given over here. So omega C has been specified, beta has been found out, C also is given. So from there you can find the value of B. So once B is also found out, the compensator transfer function is given the standard form. So put in B and put in beta. This is your compensator transfer function. So here we have also seen a direct problem in which a lag compensator has been found out. I will not be using the word design because there was not much of design in that, but we just found out the values given that the amount of lag from the compensator and the amount of attenuation required from the compensator are actually supplied. Somebody tells you or you already decide on that, then you can mechanically calculate the value of B and beta and hence get the transfer function of the compensator, lag compensator. So now we actually come to the principle for lead compensator design. Now tell me one thing, when is your theory class, when are your theory classes ending? Do you have theory classes next week as well? Does anybody know when your session is ending? পরীক্ষা কবে থেকে শুরু? Yes ma'am means what? You have theory classes next week, is it? If so, if you do have theory classes next week, what I'll do is we can continue with this particular thing in the theoretical result 27th. আচ্ছা 27 মানে আরেকটা ক্লাস পাবো, তাই তো? আরেকটা ক্লাস পাবো। I do have a few of the components, control system components also, which have to be taught. But what I will be more interested in doing is at least this thing. You should, attend a class so that we can actually learn this how to design the compensator. Whereas as far as the components are concerned, some descriptive parts, not too much of sort of, I mean, it's not very intensive as such, just description, general description, etc., etc. Things are there. You more or less understand at least 80% or 90% of what is written over there without attending a class. Whereas as far as the compensator design is concerned, I would be wanting to actually do it with you. So if you do agree and allow, I can continue today itself, or we can do it in the next week class that we have, and that single class. The actual design for I mean, control systems will be now done with the help of whatever we have done so far. So should I continue? No problem with if I continue, or does anybody have a problem if I continue? Class নেই তো এখন তোমাদের.
লাঞ্চ করবো ম্যাম।
Should I continue? হ্যাঁ কি বলো? What happened, Nurjan?
লাঞ্চ টাইম, লাঞ্চ করতে হবে তো।
ও লাঞ্চ করতে হবে। ঠিক আছে, লাঞ্চ খেতে খেতে শোনো। অবশ্য what I have is any other person who has a problem. Okay, let us stop the class today. This actual, I mean, the design as such will be what is going to be done next. So I will really take about another 1 hour at least for this. So since yes, it is almost 2 o'clock, I'm not prolonging this. I'll continue in the next class. That would be next week. So let me take the attendance. I'm finishing off today. Okay, so the actual design of the compensator will be done in the next class, which would of course be a continuation from today's class, but not I mean, not as mechanical as we have been doing in this class, meaning that in today's class most of the expressions that we had derived were more or less, I mean, theoretically you can find it, but over there we would be having certain considerations to make. Where is the stop?